Okay, today we're going to look at simple gas laws and then also the ideal gas law. So when we're looking at gas laws, the first set we're going to look at, we're going to be changing things about gases. So we're going to have equations, we're going to have an initial pressure, and then we're going to change the pressure. We're going to go through these fairly quickly because these are just plug and chug equations. There's not really much thinking. And what we're going to look at is the thing between temperature, pressure, volume, and the moles. So all those kind of things. The first one we're going to look at is Boyle's law. And Boyle's law, who you've seen last year, and it looks at the difference between pressure and volume. And if you look at this, there is what's called, an indirect, or indirectly proportional to the pressure. So as you change your pressure, if you increase your pressure, that means that your volume would have to go down. And if you think back, I'm not there, so we can't do the vacuum pump, but when you decrease the pressure of the vacuum pump, if you remember from last year, the balloon got a lot bigger. So the pressure went down, the volume went up. And if you want the equation, since you'll probably use it, if you remember that, it's P1 V1 equals P2 V2. So you use that equation if you're just dealing with pressure and volume. If we look at a graph like that, it's an indirect one, so we have the asymptotes on either end. So we have this nice little curve, it starts curving out. And then we get another asymptote on this side without that little blip at the end. This is actually how we breathe. So this is the diaphragm. What your diaphragm actually does is it'll either cause our lungs to expand or compress, and it actually forces air in and out using this thing. So what you're really doing is every time you breathe, you're using the gas laws. All right, the next one we're going to look at is Charles' law, and basically what we're looking at for this one is the difference between pressure and temperature, and this one is directly proportional. And if you remember from last year, we did the soda can, and we heated the soda can up, and we got the temperature pretty high. And then we cooled it down all of a sudden, and then all of a sudden the pressure went really low, and the can crushed itself. So if we have this relationship, it's a V1 over T1 equals V2 over T2. And remember, temperature must be in Kelvin. You have to put it into Kelvin, you may have to take it out of Kelvin, but you have to have it in Kelvin. And if we were going to graph this, our volume versus our temperature, it would just be a straight line. There is also this thing called Avogadro's hypothesis, and he basically said that if you have the same number of molecules of a gas, they're going to take up the same amount of space if they're in the same conditions, so same temperature, same pressure. So if you look here, we have helium, nitrogen, and we have methane. Different masses, but same number of molecules, and the same pressure, same temperature, and you'll notice they're all 22.4 liters. So even though they're different masses, since they have the same number of molecules, since they're all 1 mole, they're going to take up the same space. And this is a big one. 1 mole of any gas at STP, and STP is standard temperature and pressure. And you'll hear STP is being referred to frequently. But please notice that their masses are different. Nitrogen doesn't weigh the same amount as methane, and so on and so forth. So keep that in mind. All right, and then the last guy, you probably remember him, Gay-Lussac. He was looking at volume versus temperature, and what he found is that very similar to Charles, that there is a direct relationship. So they are directly proportional. And if you think about it, if you have a test tube, you have a rubber stopper in the top, you start heating it up, your temperature goes up, the volume's going to increase, and it would pop the rubber stopper right off. And again, if we were going to graph this, our P versus our T, we would get a nice straight line. And our equation's P1, T1 equals P2, T2. So last thing we're going to look at is what do we do when we put them all together before we do a couple problems. So we have them all separately, and that's great, but we really are looking for something that kind of can help us with everything. So what we're going to do is, if you remember, we combine them, and we get to combine gas law P1 V1 over T1 equals P2 V2 over T2. This is given to you on the AP test. It's in that packet. As long as you know it, as long as you can use it, you're fine. So we're going to do a couple problems so you have the answers, and then we'll move on to the ideal. So you have to be able to read them and see what's going on. So if we look here, we have a sample gas at 83 degrees Celsius and a volume. So we have a temperature of 83 degrees Celsius, and right away we change that to Kelvin. And we have a volume of 1,470 meters cubed. And then it says at what temperature in degrees Celsius, so that's our question mark. And if we change our volume, so our V2. So if you look at the equation up there, the combined gas law, we only need the V's and the T's. So I'm just going to get rid of the P's, and we're going to use V1 over T1 equals V2 over T2. And if we plug that in, we have 1,470 meters cubed over 356.15 Kelvin equals 1,250 meters cubed over X. When we solve for X, we get 302.8 Kelvin, which is 29.70 degrees Celsius, or 30 degrees Celsius. So you have to be able to read the problem, say what are my variables, and then what equation do I need. All right, next one. We have, before a trip, the car, it should say the pressure in a car tire was 1.8. At the end, the pressure gauge is 1.9. We want to know what's the new temperature. So again, we're going to say what do we have? So our P1 is 1.8 atmospheres. And they're telling us our T1 is 21 degrees Celsius, or 294.15 Kelvin. Our P2 is 1.90 atmospheres, and we're looking for T2. So again, you have to look at your equation, say I'm only dealing with P and T's, so I'm going to use my P1 over T1 is P2 over T2. You plug them in, solve for T2, 310.49. That's Kelvin. So we subtract that out and we would get 37 degrees Celsius. All right, next one. We have a sample of oxygen. It occupies 10 liters. That's a volume, so that would be our V1. And it has 790 torr. 790 torr. So that's P1. And it says, what pressure would it occupy? 13.4 if the temperature did not change. So our P2 we don't know. And our V2 is 13.4 liters. So we're going to use that equation P1 V1 equals P2 V2 to solve it. And when we're all done, if we solve it, we're going to solve for P2. Excuse me. We should get with sig figs 590 torr. And then last one that we're going to look at. So there must we have 12 liters, 240 degrees Celsius, and a pressure. So this one have to be careful because we know a lot. So our V1 is 12 liters. Our T1 is 240 degrees Celsius, which is 513.15 Kelvin. And our P1 is 80 kilopascals. Our P2 is 107 kPas. Our V2 is 15 liters. And our T2 is what we don't know. So just be careful with these because you have to make sure that everything matches. If your volume is in liters, your V2 has to be in liters. If your P1 is in kPas, your P2 has to be in kPas. It's the easiest thing to kind of mess up, so just be careful. This one, P, V, and T, means we're going to use P1, V1 over T1, P2, V2 over T2. So you plug everything in. Now you'd have to algebraically solve for T2, so you need some algebra. Our T2 is 857.9 Kelvin, or 580 degrees Celsius. So these are just a review from Chem 1. This should not be difficult. You want to make sure you can do these.